Alrighty, y'all, back at it again. We're going on to Recitation 7 today, and I hope that Quizam went good for everyone. Didn't go too great for me, but we're moving on, and we're looking at question 1 for Recitation 7. So we're trying to find the ratio between the flux on two concentric circles, two concentric spheres, sorry, when one has twice the radius of the other. So what I'm going to do is so what the flux is, if we just look at it in terms of it's the electric field crossing any point times the and it's going to be times the area, right? So the surface area of a sphere is 4 pi r squared, right? It's not a dot product. It is a dot product, but I'm just looking at it in terms of that's the area, that's the field. Generally, this is what we're looking at. So if we double the radius, it's going to be the same electric field, still caused by that same charge, but it's going to be 4 pi 2r squared, right? But now we can break up this electric field a little bit more, because for this one, any point on the sphere is going to have that charge. Oop, that's a G, not a Q. It's going to have that same charge, and we're going to divide by the radius squared, right? And that's still times 4 pi r squared. So our r squareds are actually going to cancel, right? Then we go to the electric field on this, for the larger circle, it's going to be KEQ, but now it's still 2r, because again, it's twice as far away, squared, times 4 pi 2r squared. And again, our 2r's are going to cancel. So the ratio between this thing, which is KEQ 4 pi, and KEQ 4 pi, is just 1, because they're the same. And it also holds true if we look at Gauss's law, where the flux is equal to the enclosed charge divided by this epsilon naught, because both of these concentric spheres, they're going to have that same point charge in there. So if the flux is going to be independent of their radii, then it makes sense that it's just the charge and it's going to be the same for each of the spheres. So that's what I put for my answer here is 1. I kind of spoiled it when I showed the question at the beginning. We're going to move on to question 2. And again, a little bit of a spoiler on there, but it's the same kind of idea. If the electric flux through a closed surface is 0, then the electric field is 0 at all points on the surface. So when we have, just like if we have this cross section of some enclosed surface, right? Then we have a point charge out here, say that's negative, why not, right? So what we're going to have, actually no, we're going to make it positive, because that's fine. We're going to have the field lines from this going like this, blah, 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 going out in all directions like that. The ones that enter this, the closed surface, they're also going to be exiting right on the other side, so it's going to cancel out, and that's going to give us our 0 electric flux through this entire closed surface. But the electric field at this point on the surface still has a value. It just cancels with this value. So the electric field at the point is not 0, but the total electric field passing through the entire closed surface is 0. So that's why this is false. So it's 0, then the electric field is 0 at all points. It's not going to be 0 at all points, or it doesn't have to be 0 at all points. All right, and I'm just going to go through question 3 real quick while we're here, because this is another kind of short one. Because all we're going to do is we're going to look at Gauss's law. So again, we have our flux is equal to the enclosed charge divided by this epsilon naught, that epsilon naught there. So since we have our 10 microcoulomb charge, which that is, 10 to the negative 5th coulombs? Yeah. And since it's given, it's at an unspecified location, which first of all makes trying to figure out the actual, summing up the electric fields and the flux for each of the faces. That makes it a very difficult problem. But since it's inside a cube, and a cube is closed because it's like a whole shape, right? And it doesn't even matter that it's 2 centimeters wide, because again, our flux is going to be independent of the size, like we saw with the circles. So we start with our charge, we have that epsilon naught. So really our flux is just going to be equal to this charge, 10 to the negative 5th, over that epsilon naught, which is 8.85 times 10 to the negative 12th. And if you multiply all that out, you're just going to get, or I guess divide, but whatever. 1.129943503 times 10 to the 6th, which is going to round to 1.13 times 10 to the 6th, which we can see is our answer right here. And that's in Newton meters squared per coulomb, which is our unit of flux. All right, thank you all again for watching, and let me know if you have any more questions. I know I went through the first 3 kind of fast. That's just because they seem to be a little bit more conceptual, so it had to do more with, so there wasn't a lot of math intensive or any kind of integrals to walk through. So let me know if you have any more questions or if you want any other problems explained, because I guess Sydney explains stuff.